talking about single loop analysis, KVL and KCL a little bit more. We're going to do a few more examples to just make sure it actually sinks in and we know how to just do problems using like these two methods. And then we're going to like move on to basic connections of basically like a resistance, how they can actually be connected to each other. And if we have like them in some certain ways, how we can simplify them down to like a circuit that's easier to analyze. But before we get started, let's just have like a quick review of what we talked about before. So the very, very first thing that we talked last time was KVL and KCL, Kirchhoff's current law and Kirchhoff's voltage law. KCL basically stated that if I have any node in a circuit, the amount of current that's going in is the exact same as the amount of current that's going out. So amount of current going in is the same as current going out. And we said we can actually state that in like another way by saying if I add them up, add all the currents up with their corresponding signs, it should add up to zero. So equivalently, we can set the algebraic sum of currents at any node must be zero. And for this, we had like this convention that we said, like if we enter a node, if the current enters a node, the sign we consider for it as positive. And if we exit a node, then the sign must be negative. Again, this was our convention. We could do it reverse and nothing would change. And if we wanted to have like this like pictorially, let's just say this is our node. I have a bunch of currents going in. Let's just call this I1, I2, and I3. I know I1 and I3 are going in, so they should have positive signs. But I2 is going out, so it should have negative sign. So it should add up to zero. We also had like KVL, which is stated in any closed loop in the circuit. The algebraic sum of all the voltages should be zero. So in any closed loop, the algebraic sum of all voltages should be zero. And for this, we had like this convention that if we're looping around whatever direction that we consider, if we encounter the positive side, we consider that voltage to be positive, and we're encountering negative, it means the voltage is negative. So encountering positive, then voltage is positive. Encountering negative, then voltage is negative. Pictorially, if I have like a circuit that looks like this, for example, let's just call this V1, this is V2, and this is V3. Let's just consider the clockwise direction. So if I go here, I have plus V1 minus V2 minus V3 equals 0. And as we said before, this direction does not really matter. I can have counterclockwise, and I still get the exact same equation. Let's just like work it out. If I have like the counterclockwise, I have negative V1 plus V3 plus V2 equals 0. So if I multiply everything by negative 1, nothing changes because like this side is 0. I'm going to have V1 minus V3 minus V2 equals 0, which is exactly the same as this equation. So as long as we stick to this convention that we have, it does not really matter like what direction we're considering to just loop through a circuit. So let's just do like a quick example and see like how it works. Example. Let's just say I have this circuit here. I have a dependent voltage source. The value of this voltage source is 4 times Vx. So it's a dependent voltage source controlled by a voltage in the circuit. So I have to tell you like what this V of X is. I have an independent source with value 6 volts. And let's just say I have another independent source here, another one over here. And let's just say voltage across this element here is Vx. And I have another element here where the voltage across it, let's just call it V3. Voltage across this guy over here is V2. And here is V1. Again, all these like polarities that I gave you over here, it's given in the problem. So the question is asking us what is V1, what is V2, and what is V3. So the way that we can solve this is that since we're asking for voltages, the easiest way to think about this problem is to write KVLs because KVL is actually producing voltages. So let's just call this loop over here loop 1, this loop over here loop 2, this one over here loop 3, and this one down here loop 4. I consider all of them to have like clockwise direction. You do not really have to do that, but I'm just doing it for the simplicity. So let's just write the KVL for loop 1. Again, what I do know is that like if I go around a loop and I added up all the voltages with their sign, it should add up to 0. So if I start here, I have minus 12 plus 4 plus Vx. That should be 0. So from this, I can compute Vx to be 8 volts. Now I know Vx, I know exactly what the value of this dependent voltage source is. So let's just write KVL for loop 2. So if I write the KVL for loop 2, again, I considered the clockwise direction, so I just need to add up all the voltages with their sign. So I have minus 4 minus V1 minus 4 Vx, and that should be 0. But I already know this Vx is 8 volts. So from this, I can compute V1. It turns out V1 is minus 36 volts. I can do the same thing for like loop 3. So let's just do KVL for loop 3. So if I do that, again, I'm going clockwise. I just need to add up all the voltages. So let's start with the independent source. So I have 6 plus V2 plus 4 Vx. That should be 0. Therefore, V2 is minus 4 Vx minus 6. I know this Vx is 8 volts. Therefore, V2 is minus 38 volts. Doing the same thing for loop 4. Let's start by V2. I have minus V2 plus V3 minus Vx equals 0. I know V3 is Vx plus V2. I already computed Vx. I already know V2. Therefore, V3 is minus 30 volts. Again, all I did was just wrote KVLs for the loops, and I basically stick to the convention that we had. Let's do another example to see how it works. Let's just say I am given a circuit that looks like this. Example, I am given a circuit that looks like this, 12 volts. I have a 3K resistance. I have a dependent source with the value 2000 IS. So it's a voltage source, but its value is being controlled by a current in the circuit. So I have to tell you like what it is. So let's just assume this is I of S. And it's followed by another 5K resistance. And the question is asking you to find voltage across this 5K resistance. So that is the question. Well, to be able to like find this V out, we have to know current through this 5K. So let's just write a KVL for this loop and see like how it works. So let's assume this is the direction that we have. I have minus 12 plus voltage across this 3K resistance minus 2000 IS plus voltage across this 5K resistance. And because of the KVL, I know it should add up to 0. So this is basically my KVL. If I look at this, I have 3 variables in this equation, but I only have one equation. So I have to write everything in terms of like one thing. Because of Ohm's law, we know V across 3K is Ri. So it's 3K times Is, because current through this 3K resistance is Is. We can apply exactly the same thing for this 5K resistance. So V across this 5K is 5K times. Again, remember this I of S is going to flow through here, and it's going to be exact same when it's flowing through 5K. So current through that would be I of S. Now using these two equations, I can plug in back in here. And now I have an equation that everything is in terms of I of S. So what I have here is minus 12 plus 3000 IS minus 2000 IS plus 5000 IS. That should be 0. If I solve for IS, I can see IS is 2 milliamps. Basically 2 times 10 to the power minus 3. But that's not the question. The question is asking me what is V out? Well, again, to find V out, I know V out is voltage across the 5K resistance. And I know because of the Ohm's law, the relationship between V and R and I is Ri. So I have 5K times 2 milliamps, which is going to be 10 volts. So that's basically what it is. Now we know how to analyze simple circuits. What if my circuit is a little bit like more complicated? How can I solve circuits that are like more complicated? One of the simple things that we can do is to basically simplify down the circuits given the connections that we have in the circuit. So we have to know the connections in the circuit. So if I have a resistive circuit, which basically has a bunch of like resistors together, these resistors can be connected to each other in 3 different ways. The first way is that they're connected in series. The second way is parallel. So they're connected in parallel. And the last way that they can connect is neither series nor parallel. So they're just like connected to each other in a completely different way. So it's neither series nor parallel. So let's understand like what these actually mean. So let's start off by series. Series connection. We say a bunch of resistors are in series if basically they're back to back. So we call R1 and R2 in series when they're back to back. And by that, I mean the end of one is the beginning of the other one. So we call R1 and R2 in series if they are back to back. Also, current through R1 should be exactly the same as current through R2, right? So to summarize it, we have to check two conditions. The first condition is R1 and R2 are back to back. The second condition is current through R1 is exactly the same as current through R2. So if I call this I of R1, this I of R2, they should be exactly the same. How about the voltages across R1 and R2? Are they supposed to be the same? The answer is no. Voltage across R1 and R2 are different. And as a matter of fact, voltage across R1 and R2 are proportional to the value of R1 and R2. And we can simply compute it. So if I want to compute voltage across R1, it's R1 times I of R1. V across R2 is R2 times I of R2. And since we know I of R1 is exactly the same as I of R2, let's just call them I. V of R1 is going to be R1I. V of R2 is going to be R2I. So as you can see, voltage across R1 is proportional to the value of R1, and voltage across R2 is proportional to the value of R2. Okay, so the voltages across R1 and R2 are not the same. And the only time the voltage across R1 and R2 are the same is when R1 is exactly the same as R2. Otherwise, the voltages across R1 and R2 are proportional to the value of R1 and R2. What we do know, however, is current through two resistors back to back or in series should be the same. We can basically replace this R1 and R2 by an equivalent resistance. So let's just call voltage across this one V of R1, voltage across this one V of R2. What we're hoping is to replace the whole thing here by an equivalent resistance. And let's just call voltage across this equivalent V equivalent. Let's just call this point A, this point B. Therefore, this is going to be A, and this is going to be. As you can see in this graph, we know V equivalent is exactly V of R1 plus V of R2. Because V equivalent is the voltage between A and B, and voltage between A and B in the first graph over here is V of R1 plus V of R2 because of the KVL. Since R1 and R2 are in series, I know the current through R1 is exactly the same as current through R2, and therefore the current through this equivalent should be the exact same. So if I write basically the Ohm's law for each one of these equations. For this one, I have R equivalent times I equals to R1 times I plus R2 times I. And since I's are the same, I can cancel them out. And what I end up getting is R equivalent is R1 plus R2. So if I have two resistors back to back, I can replace those two by the summation of them. I can generalize this to any number of resistors that I want. So let's just say I have R1, R2, all the way to Rn. Let's just say I have n resistors. They're back to back, and current through R1 is the exact same as current through R2, is the exact same as current through Rn. Let's just call them I. If I wanted to replace this by its equivalent, because of what we just computed, our equivalent would be R1 plus R2 all the way to Rn. And we know the current through this guy is still this I over here. Okay? So let's just do like a quick example and see like how this can become handy for us. Example. Let's just say I have a very simple circuit that looks like this. There is a voltage source. It's followed by two resistors back to back. R1, R2. Let's just call this Vs. Let's just call voltage across R1 V of R1, voltage across R2 V of R2. And let's just call current through it I. Okay? And the question is, given Vs, what are VR1 and VR2? Right? Well, we know how to do this. Let's just write a KVL here and see like how it works. So if I write a KVL, what I have here is V of R1 plus V of R2. That should be the exact same as V of S. This is basically the KVL. But what we do know is that V of R1 is R1 times I, V of R2 is R2 times I, and V of S is just a number it's given to us. Therefore, we can compute I from here. So if I factor out I can compute I to be Vs divided by R1 plus R2. Which again, it matches our intuition because R1 and R2 are in series. I can combine them and replace them by R1 plus R2 as our equivalent. And then we can simply just write Ohm's law, right? Now, if I want to find V of R1, V of R1 is R1 times I, which is going to be R1 divided by R1 plus R2 times V of S. If I want to compute V of R2, R2 is R2 times I, which is going to be R2 divided by R1 plus R2 times V of S. What's very, very important here that you should pay close attention to. If I want to find voltage across R1, voltage across R1 is proportional to the value of R1. And voltage across R2 is proportional to the value of R2. This circuit is actually very, very important. It comes very, very handy for us, so we give it a name. And since we're actually dividing like the voltage between like R1 and R2, we call this circuit voltage divider. So whenever I'm talking about like a voltage divider circuit, what I mean is that like we have like a voltage source that's followed by two resistors back to back. And we know if you want to find like voltage across like one of these resistors, the voltage across that specific resistor is proportional to the value of that resistor divided by the summation of like all the resistors, time basically the source. We can generalize this. We can simply generalize this to like n resistors back to back. So let's just generalize it quickly. Generalizing voltage divider. So let's just assume I have a source, voltage source, and it's followed by n resistors. Let's just call them R1, R2, all the way to like Rn, right? So if I want to find this I here, let's just replace the whole thing here by its equivalent. So my circuit would look like this. And since all these resistors are in series, I know this R equivalent is R1 plus R2 all the way to Rn. Now, if I want to find I know I is Vs divided by R1 plus R2 all the way to Rn. Now, if I'm asked to find voltage across any of these resistors, let's just call it like V of Ri, which is the ith resistor in this circuit. I know the value of this is Ri times I, which is going to be Ri divided by R1 plus R2 all the way to Rn times Vs. Again, what's important here is that the value of the voltage across any of these resistors is proportional to the value of the resistance divided by the entire thing, multiplied by the source voltage. We can even make this thing like a little bit like more generalized. So let's make it even like one step more generalized. So this is basically like the most generalized voltage divider circuit that you can get. So I have a bunch of like voltage sources. Let's just say I have M of them, and I connect them all to N resistors back to back. What we can do here is that we can replace the whole thing here, according to the KVL, by another voltage source. And since all these like voltage sources have like the same polarity, so the negative is on the bottom and the positive is on the top. So the value of this thing is going to be Vs1 plus Vs2 all the way to Vsm. And this is due to KVL. We can replace this guy over here to the equivalent, which is going to be R1 all the way to Rn. And therefore, we can find this I just by using Ohm's law. We know I is, let's just call this V equivalent over R equivalent, which is going to be Vs1 all the way to Vsm divided by R1 all the way to Rn. Right? Now, if I'm asked to find voltage across any of these I's, because of the Ohm's law, that's Ri times I. We already computed I can plug it back in here. So I have Ri divided by R1 all the way to Rn times VS1 plus VSM. So again, what's very important here is that voltage across Ri is proportional to Ri divided by the whole thing. But this time, instead of having like one source, we have like a few of them. So I replace that value by the algebraic sum of like the sources. Okay? So let's just do like a quick example with numbers so we know how it works. Example. Let's just say I have a circuit that looks like this. This is R1, which is 3K. I have R2, which is 6K. And the question is, what is V across R1 and what is V across R2? Well, because of the voltage divider, I know V across R1 is proportional to R1 divided by R1 plus R2 times the source. So it is 3 divided by 3 plus 6 times 9, which is 3 volts. If I want to know V across R2, that is proportional to R2 divided by the summation times Vs. So it is 6K divided by 3K plus 6K times 9. So it's going to be 6. And as you can see, if I add up V of R1 plus V of R2, that actually gives me my source value. So this is actually correct. Right? Another type of connections that we have is parallel connection. We say two resistors are in parallel. Two resistors are in parallel if they satisfy the following. First, they should have the exact same head and tail. So they share the exact head and tail. Second, voltage across the first one should be exact same as voltage across the second. So if I want to show it like pictorially, I call R1 and R2 in parallel if they have like exact same head and exact same tail. And what I know is that like voltage across this R1 is exactly the same as voltage across R2. Let's just call this V of R1. This is V of R2. We know exactly V of R1 is the same as V of R2. How about the current? How about the current through R1 and R2? The answer is no. The current through R1 is not the same as current through R2. What we do know is that voltage across R1 is exactly the same as voltage across R2, but current through them are not the same. The only time that the current through R1 is the same as current through R2 is when R1 is exactly the same as R2. Otherwise, in general, I of R1 is not the same as I of R2. So let's see what happens here. I know V of R1 is the same as V of R2. Let's just call that like equal to V. Because of this, if I call this I, that's basically the current that's going to this node. What we do know is that I is I of R1 plus I of R2. So keep that in mind. And let's just say I have these two resistors. This is called this point A, this point B. And let's just say I wanted to replace this by an equivalent resistance between A and B. Well, this is I, then this is going to be I. Let's just call this I of R1. This is I of R2. So if I have like the equivalent resistance, this I over here should be I of R1 plus I of R2. But I know I of R1 is V across R1 divided by R1, and V and I through R2 is V across R2 divided by R2. And if I have like an equivalent resistance, I know the voltage across the equivalent should be exact same as voltage across R1 and voltage across R2. So I can write this I as V equivalent divided by R equivalent. But since they're in parallel, V of R1 is the same as V of R2 and it's the same as like V equivalent. So I can cancel these out. So what I end up with is 1 over R equivalent is the same as 1 over R1 plus 1 over R2. Similarly, I can generalize this. So if I have n resistors that are sharing the exact same head and tail, so if you look at all these resistors, they have like exact same head and they have exact same tail. And I know voltage across R1 is the same as voltage across R2 all the way to voltage across Rn. If I want to replace this by an equivalent resistance, the value of this resistance is going to be computed through this formula. 1 over R1 all the way to 1 over Rn. Let's just go back to like this simple two resistors. We can simplify it down. I can basically like find a common denominator and just do like a cross multiplication, and I can get like a simple formula for R equivalent, which is going to be R1, R2 divided by R1 plus R2. So I can either use this formula over here, or I can use this formula. However, I cannot really do this for any number of them. It's going to be a little difficult. So we're just going to stick to this. And if you have like a bunch of like resistors, we're going to stick it to this formula and we're going to look at the inverses. Another thing I wanted to like point out is that if I have a bunch of like resistors in series, what we're adding up is the value of the resistors. However, if we have like a bunch of like resistors in parallel, what we're adding up is the inverse value of like the resistors. But if you guys recall, we had a name for these things. These were like conductances. So for resistors, if they're in parallel, we're adding up the conductances. And if they're in series, we're adding up the resistances. This is just a small point to pay attention to. Again, let me just have like a quick summary of like what we discussed. Summary. If we have series connection, let's just say I have two of them. What I do know is that I through R1 is the same as I through R2. Let's just call it I. However, voltage across R1 is not the same as voltage across R2. And if I wanted to find the equivalent resistance is R1 plus R2. For the parallel connection, if I have R1 and R2, I know R1 and R2 should share the exact same head and tail. What I do know about them is that V across R1 is the same as V across R2. Let's just call it V. However, I across R1 is not the same as I across R2. And if I wanted to find the equivalent, our equivalent should be computed using this, right? So let's just do like a quick example as well. Let's just say I have a circuit that looks like this. I have a current source with value of I of S. Let's just say this I of S is given to me. And I have R1 and R2 in parallel with that. And the question is, I want to find this I of R1 and I of R2, right? Well, we know voltage across R1 is the exact same as voltage across R2 because R1 and R2 are in parallel. So let's just write a KVL at this node, KCL at this node. So KCL. So if I write a KCL, I know I of S should be exact same as I of R1 plus I of R2. Whatever goes in should be the same as like whatever's coming out, right? But what is I of R1? Well, I know I of R1 is V across R1. Let's just call that V of R1 divided by R1 plus V across R2 divided by R2. However, we know like V of R1 is exactly the same as like V of R2. So I can write that as V divided by R1 plus V divided by R2. Now I can factor out this V. So I have V times 1 over R1 plus 1 over R2, right? I can simplify this down. I can write this as R1 plus R2 times R1, R2. Therefore, I can compute V, which is V across R1, same as V across R2, to be I of S times R1 plus R2 divided by times, it's going to be R1, R2 divided by R1 plus R2, right? So what are we looking for? We're looking for I of R1. I of R1 is V divided by R1. So it is I of S times R1, R2 divided by R1 plus R2, the whole thing divided by R1. R1 and R1 cancel, so it is R2 divided by R1 plus R2 times I of S. We can do the same thing for R2. It is V divided by R2, so it's IS times R1, R2 divided by R1 plus R2 times 1 over R2. R2 and R2 cancel, so I have R1 divided by R1 plus R2 times X. What I would like for you to pay close attention to, unlike the voltage divider circuit, if I wanted to find current through R1, the value of current through R1 is proportional to the value of like other resistance. And the same thing over here, the value through R2 depends on like R1. This circuit is another very important circuit, and it's called current divider circuit. Again, what's very important for the current divider circuit is that the value of the current through a resistance is proportional to the value of like other resistance, not the same resistance. Again, remember for the voltage divider, the value of the voltage for each resistance was proportional to the value of that exact same resistance. Okay? So that is very, very important. So let me quickly put these two things together. Recap. We talked about two circuits. voltage divider. And we talk about current divider. So if I have like a voltage source in series with two resistors, just call it R1 and R2, we can find voltage across R1 to be proportional to the R1 divided by the whole thing times Vs. V across R2 is R2 divided by R1 plus R2 times Vs. For the current divider circuit, I have a current source in parallel with two resistors. And if I wanted to find current through each resistance, I know I of R1 is R2 divided by R1 plus R2 times Is. And I of R2 is R1 divided by R1 plus R2 times Is. If you pay close attention, you can see like when I was driving this example for the current divider, I did not really generalize it the same way I generalized the voltage divider. And the reason for it is that like, if I generalize this to like more resistors, this is going to be a little bit like more complicated. It's going to be messy because we don't know exactly like what current is proportional to like what resistors. But the idea here is that like if I have like more resistors like in parallel, we can always like simplify them down to like two resistors and then use the current divider circuit that we have. So we don't really need to have a generalization for the current divider circuit. Okay, let's just do an example for the current divider. So let's just say I am given a current source. Uh, let's just say that the value is 3 milliamps and it's followed by two resistors, 30K and another one is 60K. And the question is like, what is current through these two? Again, because of the formula, you know, I through R1 is proportional to the value of R2. So it's going to be 60K divided by 30K plus 60K times 3 milliamps, which is going to be 2 milliamps. And I through R2 depends on the value of the other resistance divided by the whole thing times the value of the source, which is 1 milliamps. And again, it should intuitively be like obvious to us. And the reason for it is that like if the value of the resistance is like more, so we're expecting to have less current going through it. And that's exactly like what this formula is telling us, right? Let's do another example to make it a little more interesting. Let's just say I have a circuit that looks like this, followed by a 20K resistance, another 30K, and another 20K. And the question is asking us what is voltage across this 20K. So if you look at this circuit over here, this circuit does not really look like a voltage divider circuit. But what we can do is that we can combine these two. And if you combine these two things, then it would look like a voltage divider circuit. But how can we combine these two? So if you look at it, this 30K resistance is in parallel with this like 20K resistance. Why? Because if I look at it, they actually share the exact same head and the exact same tail. So if I combine these two, I can use like the formula for the parallel connection. So if I combine them, the value for it would be 30K times 20K divided by 30 30K plus 20K, right? Which is going to be 12K. So my circuit would look like this. 12 volts, 20K, 12K. And what I'm after is voltage across this. So voltage across this 12K is 12K divided by 20K plus 12K times 12, right? But here's a very important thing. This 12K over here is this 30K and 20K in parallel. So this is this 30 in parallel with 20. So if I have two things that are in parallel, what it means is that voltage across each one of them is the same as the other one, and it's the same as the equivalent. Therefore, if I want to like find V out is nothing but this V12K. And this is basically due to 30K being in parallel with 20K.